Welcome back to RPS. Thank you for visiting my channel. This channel is dedicated to sharing knowledge for quality inspectors, managers, and engineers. I hope you enjoy it. The API institution that governs petroleum safety worldwide. Every tank, pipeline, pressure vessel began as a temporary wartime committee. It was never supposed to be permanent. Today we're talking about the American Petroleum Institute. 800 standards. 140 countries. And a story that begins not with engineers, but with oil executives terrified of the federal government. Here's what we're going to cover. How a wartime logistics committee became the most powerful engineering standards body in the world. The 800-plus standards that run the oil industry. And how documents that start as voluntary end up becoming federal law. Industrial disasters that forced those standards into existence, including a tank collapse that cut off drinking water for over 1 million people. Risk-based inspection. How API killed the calendar and replaced it with math. And the climate suppression playbook API ran for 40 years, while simultaneously writing the safety rules that protect workers. All of that today. Before we get into the history, let me give you the number that matters most. Per million gallons. That was the capacity of the diesel tank that Ashland Oil was commissioning in Floreffe, Pennsylvania. On January 2, 1988, workers were filling it for the first time. The tank didn't just fail, it unwrapped. The entire shell opened like a seam splitting, and 1 million gallons of diesel poured directly into the Monongahela River. Drinking water for more than 1 million people across Pennsylvania, West Virginia, and Ohio was shut off immediately. There was no API standard in existence for the in-service inspection of existing storage tanks. The industry had codes for building tanks. They had nothing for maintaining them. We'll come back to what caused this, the exact flaw, the exact number. But hold that image as we walk through what API was, what it built, and what it missed. The American oil industry started in 1859. Edwin Drake struck oil in Titusville, Pennsylvania, and the boom was on. For 60 years after that, the industry ran on gut feelings. No unified engineering standards. No common equipment dimensions. No technical language shared across companies. Manufacturers built to proprietary specifications. Components from different suppliers didn't fit together. There was no supply chain logic. Pipeline and vessel integrity, what we would call mechanical integrity today, depended entirely on the personal judgment of senior operators. Not science. Not code. Experience. Intuition. Gut. Standard Oil's monopoly had hidden all of this. When one company controls the whole industry, you don't need standards. You just do it their way. But in 1911, the Supreme Court shattered Standard Oil into 33 competing independents, and suddenly the chaos was visible. By the outbreak of World War I, the United States was producing roughly 70% of total global petroleum output, 70%, from an industry with no national technical body and no shared engineering language. That was about to become a problem the federal government couldn't ignore. World War I changed everything. Tanks, aircraft, naval vessels, all of them needed fuel. The demand was unprecedented. The federal government recognized the problem and formed the National Petroleum War Service Committee under Standard Oil Chairman A.C. Bedford. The NPWSC successfully coordinated wartime fuel logistics across a fragmented, chaotic industry. And when the war ended, oil executives looked at what had just happened. The federal government had run their industry. It had worked. And now they were afraid. Because if the government could run it once, what was stopping them from doing it permanently? The railroads had already been nationalized temporarily. That conversation was alive in Washington. The oil industry's answer was preemptive self-regulation. Build the institution before Washington does it for you. On March 20, 1919, at the Biltmore Hotel in New York City, the American Petroleum Institute was officially incorporated. First President, Thomas A. O'Donnell. The founding members were largely the same individuals who had just served as wartime government regulators. Within 1 year, API's statistical network was so effective, tracking crude production, refinery runs, inventory stocks, that the federal government shut down its own competing databases. They didn't need to run the industry. The industry had agreed to run itself. The Formal Standards Program launched in 1924. The motivation was straightforward. Interchangeable parts are cheaper. The first generation of documents was market ordering. Equipment dimensions, drilling tools, tanks, field measurement. Make the parts fit. Make the measurements consistent. Give every operator in the country a common language. Early milestones. API 7B, 1927. Rotary drilling equipment. API 12A, 1928. The first specification for riveted storage tanks. API 25, 1929. Field measurement of production and storage. API also introduced 2 measurement units still used globally today. API gravity, the standard measure of petroleum density, still on every oil price screen in the world. And the API unit, the standard for measuring natural gamma radiation in boreholes. By the 1930s, the catalog had expanded beyond hardware into waste disposal, accident prevention, and safe practices. The technical language was taking shape. What came next was the code itself. 2 codes govern above-ground storage tanks in the United States, and they are not the same. API 650, published in 1961. This is the code for non-refrigerated carbon steel tanks. Atmospheric pressure. Max 2.5 pound per square inch gauge. Up to 500 degrees Fahrenheit. If you've ever worked a plant turnaround, walk the tank farm, written an inspection plan, you know API 650. It governs the common steel storage tanks that hold crude, diesel, naphtha, water, the workhorses of the petroleum industry. API 620 is a different world entirely. Cryogenic tanks, liquefied natural gas, high-pressure service. We're talking about structures that can exceed 300 feet in diameter, built on site, assembled in place, because they're too large to ship. At cryogenic temperatures, 260 degrees below zero, standard carbon steel doesn't bend. It shatters. So API 620 specifies specialized nickel alloys that maintain ductility in extreme cold. Both codes govern how to build tanks. Prior to 1991, there was no standard for how to inspect and maintain them once they were in service. That gap between construction code and maintenance reality is exactly what cost Floreffe its drinking water. 3 more codes, all critical. API 1104 to 1953, the dominant pipeline welding code in the United States. Welder qualification, welding procedures, weld acceptance criteria. When you want to qualify as a pipeline welder under API 1104, you don't just weld something and pass a visual inspection. You weld a test piece, and then the inspector performs a destructive bend test. They literally break the weld. They cut it apart and examine the internal grain structure, because what the weld looks like from the outside doesn't tell you what it looks like where it counts. API 510, 1958, the in-service inspection standard for pressure vessels. When it was first published, it required operators to physically open and enter pressure vessels every 10 years for inspection. Shut it down. Depressurize it. Open it. Go inside. Calendar-based. Fixed interval. Every vessel, every 10 years, no matter what. API 570, 1993. This code modernized plant piping inspection. Instead of uniform grid checks across all piping, API 570 divided systems into risk circuits based on fluid toxicity. High toxicity fluid? More inspection. Low toxicity fluid? Less. And it focused resources on high stress points, elbows, T's, rather than spreading them evenly across pipe runs that don't need it. These three codes together cover the internal integrity of the infrastructure that moves hydrocarbons under pressure. Now I want to talk about the biggest conceptual shift in the history of inspection. For decades, inspection was calendar-driven. Inspect this vessel every 10 years. Check this pipe run on this schedule. Audit this tank this year. The calendar decided where the resources went. The problem was obvious in retrospect. Low-risk equipment got inspected on time. High-risk equipment also got inspected on time. The calendar didn't know the difference. API 581, published May 2000, introduced a different framework. Risk is not a calendar problem. Risk is a math problem. Risk equals probability of failure, multiplied by consequence of failure. High probability. Catastrophic consequence. Inspect that equipment now. Low probability. Minimal consequence. Schedule it later. Put the money somewhere it matters. API 580, published 2002, provided the programmatic framework, where 581 gives you the quantitative model. 580 gives you the structure, how to organize the program, how to use institutional knowledge from your plant staff when hard data is limited. Together, they shifted maintenance from a schedule-driven chore to a risk-prioritized, mathematically defensible strategy. The calendar was dead. Here's something most people in the field understand intuitively, but have never seen explained directly. API standards are voluntary. No government writes them. No Congress votes on them. Private committees of industry experts draft them, debate them, revise them, publish them. And then the federal government adopts them. By law, federal agencies are directed to adopt voluntary consensus standards, rather than writing their own government-specific technical rules. This mechanism is called incorporation by reference. Here's what that means in practice. PHMSA, the Pipeline and Hazardous Materials Safety Administration, embedded API 1104 directly into federal pipeline regulations. 49 CFR Parts 192 and 195. That means API 1104's qualification requirements for pipeline welders are not suggestions. They are federal law. OSHA explicitly cites API 510 and API 570 as RAGAGEP, recognized and generally accepted good engineering practice. Under its Process Safety Management standard, failure to comply with RAGAGEP accounts for roughly 23.6% of all OSHA Process Safety Management citations. The private committee room, where API engineers debate inspection intervals, is one of the most consequential regulatory spaces in American industry. No votes, no hearings, no congressional record, just engineers and law. Now we come back to Floreffe, and we go inside the failure. The tank had been salvaged from another state. Steel originally manufactured for a different application. Moved, relocated, rebuilt, with no material assessment, no documentation of prior heat treatment or cutting operations. The National Bureau of Standards investigated. What they found was a 0.74-inch flaw in the steel, not a crack you could see with your eyes. a subsurface defect, embrittled by a prior cutting operation that had been sitting there, undetected, in rebuilt salvage steel. The day of the collapse was January 2nd. Temperature, 26 degrees Fahrenheit. Cold steel behaves differently than warm steel. It becomes brittle. The NBS measured the steel's impact resistance, its ability to absorb energy and stop a crack from propagating. The result, 6 foot-pounds. The minimum needed to arrest a crack in that application? 15 foot-pounds. The steel had less than half the toughness it needed. On that cold January morning, as workers filled the tank for the first time, the flaw propagated, the shell completely unwrapped. Ashland Oil was indicted under the Clean Water Act, fined $2 million. Within 3 years, API 653 was researched, written, and published. January 1991, the first standard ever written, specifically for the in-service inspection of above-ground storage tanks. The gap was closed by a disaster. Bhopal, 1984. The Union Carbide plant in Bhopal, India, released 40 tons of toxic methyl isocyanate gas. Thousands of people died. The industry couldn't ignore it. API responded almost immediately with API RP 750, Management of Process Hazards, the first API code specifically addressing the management of highly hazardous process chemicals. But the deeper lesson from Bhopal, and from 2 decades of subsequent disasters, was that the industry didn't know when its own safety systems were failing. Texas City confirmed it. March 23, 2005. BP Texas City Refinery. An isomerization unit exploded during startup. 15 workers were killed. The Chemical Safety Board's investigation found something alarming. BP Texas City had good personal safety metrics. Recordable injury rates were down. The numbers looked fine. But process safety was collapsing underneath those numbers. Equipment was degraded. Safety systems were bypassed. The indicators that measured slips and trips were hiding the deterioration of the actual infrastructure. The CSB concluded that the industry lacked the metrics to detect systemic process safety decay. API collaborated directly with the United Steelworkers to develop the response. API RP 754, published April 2010. A 4-tier continuum of process safety performance indicators. Tier 1 and Tier 2, publicly reportable. Major and minor containment losses. The lagging indicators, the harm that already happened. Tier 3 and Tier 4, internal leading indicators. Management system health. The warning signs before the harm. For the first time, the industry had a framework to see the deterioration coming, not just count the casualties after. April 20, 2010. The Deepwater Horizon drilling rig in the Gulf of Mexico suffered a catastrophic blowout. 11 workers died. 87 days of oil discharging into the Gulf. The investigation revealed something that everyone in offshore drilling already suspected but never had to formalize. Offshore complexity, the depths, the pressures, the remoteness, required an entirely different oversight architecture. What the industry needed was a comprehensive safety and environmental management system, SEMS, a framework that addressed not just individual equipment, but the entire organizational system governing offshore operations. API RP 75 formalized that framework, and the Bureau of Safety and Environmental Enforcement, BSE, directly incorporated API RP 75 into offshore federal regulations. Another private standard, another incorporation by reference, another disaster in the preamble. Now I need to tell you something that doesn't fit neatly alongside the codes and the disasters. In 1954, the American Petroleum Institute, secretly funded, Project 53. At Caltech, the project measured rising carbon dioxide levels from the burning of fossil fuels. The results were kept private. 1959. Physicist Edward Teller, one of the developers of the hydrogen bomb, stood in front of API executives at a centennial celebration of the petroleum industry. He warned them explicitly. Carbon emissions from fossil fuels would inevitably trigger a greenhouse effect, melting ice caps, rising sea levels, submerged coastal cities. 1965. API President Frank Eichert addressed his peers. He told them privately that time is running out to avert catastrophic atmospheric changes. They did not publish this. They did not act on it. They knew. 1998. The API drafted a communications plan, explicitly designed, in writing, to manufacture public uncertainty about climate science, the same strategy the tobacco industry used on lung cancer. API paid one researcher $1.25 million over 14 years to produce anonymous papers attributing global warming to solar activity, not fossil fuels. Solar activity. The same institution that wrote the codes protecting workers from refinery explosions was systematically funding the suppression of the science of what those refineries were doing to the atmosphere. Let's put a number on it. API generates over $239 million annually. Since 1998, it has spent over $127 million lobbying against environmental regulations and climate legislation. 2009. API organized energy citizens rallies, events where member companies bust their own employees to simulate grassroots opposition to climate bills. The people who worked at the refineries bust to rallies to oppose legislation that might have reduced their own risk. API also paid a public relations firm $29.3 million to build artificial local political support for fracking operations. This is the core contradiction at the heart of API. The same institution, the same building, writing codes that protect workers, and funding campaigns against the science of atmospheric harm, safety stewardship, and political combat, running in parallel for over a century. 3 things to carry out of this. First, API transformed a chaotic, heuristic-driven industry into a standardized, globally interconnected infrastructure system. Nearly every foundational code in that system, API 653, API RP 754, API RP 75, was written in response to a disaster that exposed the absence of a standard. If you're an inspector today, the codes in your hand exist because someone died without them. Second, through incorporation by reference, voluntary API standards become enforceable federal law without a congressional vote, without a public hearing, without a regulatory comment period. The private committee room is one of the most consequential regulatory spaces in American industry. Understand who's in that room. Understand what they're deciding. Third, API operates a profound core contradiction. Chief safety steward, chief political defender, simultaneously writing codes to prevent the next catastrophe, while funding campaigns against the science of long-term harm. Every standard has a story. This one has too. Thanks for watching. The codes in that list on screen, they were written by people who looked at disasters and said, never again. The question that history keeps asking is whether the institution that writes the safety rules has the willingness to live by its own findings. Every standard has a story. This has been episode 03. Thanks for watching, and look for the next video on AWS.